Good job. Okay, so we've got a scalar projection, and so we call a scalar projection, we refer to that as a component, and it's often shortened to component. Okay, now if we're doing the projection of A and B, so let's say we've got a simple one, and B, assuming they're coloured in, of course. The language can be very confronting here, but the clue is in the way that A and B go together. Okay, so it's very, very important that you get this. Okay, so if I say find B onto A, the way that it comes up here in shorthand is that we put the little a down here as the subscript and the big B up here as though we're operating on B. Okay, so it's very, very important that you get that correct, because this here is a match to that language, and if I say A onto B, they will change. Alright, so it's very, very important that you get that correct. Okay, okay, now in terms of the component A onto B, what does it equal to? No, I just said it wrong, didn't I? B onto A. Okay, but did you get that from, is that something that it's familiar with you? Okay, then our vector, these should be squiggly lines. They should all be squigglies. Okay, so then the scalar projection, or the number projection, is going to be the dot product of A and B divided by the unit vector in A. Alright, so this, how you visualize this B goes to this B, there's only one, and the unit vector A divided by the unit vector is effectively scaling scaling A. Alright, so if you change it from A onto B, then you're going to have, let's just do that in a different colour. So let's just peel that off here. Find A onto B. We would have comp A subscript B, and the implication there is that we would have, now I've put them around the wrong way deliberately. Okay, see how it changes? So it's very important that you get that right. Okay, it's very important that you get that context right. Alright, so what's the magnitudes and the dot products? So the magnitude of A, sum of products, minus 4 times 1, 3 times 1, we get a number, minus 4 plus 3, okay, minus 4 plus 3. Alright, the magnitude of A did it again, didn't I? So now we've got those two pieces of information, we can go ahead and do the component form. B onto A is going to be -1 divided by the square root of 10. That's it, that's the component. So the scalar projection gives you a number, doesn't it? What do you think the projection is going to be? The vector projection. So if the scalar projection gives you a number, what's the vector projection? If the scalar projection gives you a number, what's the vector projection? The vector projection is a vector. Good. It's not just a number, it's a vector. Thank you, mate. Okay, so sorry, I just had to open the chat because you weren't speaking to me, which is fine. Alright, so we need to now consider how to do the projection. So the vector projection uses the previous result. Okay, so it depends if you've got to do the work all again, if the language is the same. Okay, so in this case here we're finding the B onto A again. So the way that we set the projection up is the projection. Who can tell me? B onto A, so B is the big one, A is the subscript. Okay, and this now, so that's the same rule we applied for the component, is the component projection, the scalar projection of B onto A, multiplied by, who can tell me? The vector A. Now not the dot product, just the multiplication. Okay, and the vector A is going to be the unit vector. I should put that. Sorry, I'm going to great lengths to pull this out all this way. So it'll be A over A magnitude. Alright, so what's the difference? Up to this point here, the component AB is exactly the same, and all you're really doing is scaling the vector by its magnitude, which gives you the unit vector. So notice the link there. So we are multiplying by a vector, it's just that we're multiplying by the unit vector. So in our particular case, we've got all of those things together. The only difference now for the projection onto A from B is that the previous result gave us this bit, okay, as -1 on root 10, and then we need to do the unit vector. Now, times, sorry. I'll take that off. I'm just going to use spaces to denote times. So A was the vector 1, 3. And what was the magnitude of A? Oh, there it is, root 10. So coincidentally, we have another root 10. So I can do 1 over root 10. Now, could have put it underneath. Okay, I could have put it underneath like that, but that's also how I've written it. Sometimes you can do this expansion straight away. I could have written it as all of that, but instead of doing that, I've got an easy product. So I've got a minus 1 root 10 times a 1 on root 10 times our vector. Now this is clearly root 10 squared. Root 10 squared is just 10, so it's minus 1/10 times 1, 3, which we can put as, now we can do an expansion, minus 1/10 minus 3/10. Now, and finally 1/10 is minus 0.1 minus 0.3, and that's our final result. That's our vector projection. So you can see it's been scaled for the unit vector. Okay, so that little vector sits as the projection for this other one, 1, 3. So what do they look like? Let's see what the geometry of those looks like. 1, 3 and minus 4, 1. X and Y. Minus 4 and 1 again. And that makes sense because the angle, although I've made it look like it's a 90 degree, it's actually greater than that. So this is B. And what we would have to do to interpret this is we would have to draw, let's draw it in a different colour. Now, negative 0.1 is X. So I'm exaggerating it a little bit. Negative 0.1. And negative 0.3. So negative 0.3. Sort of hanging down here like this. So that's our unit vector of our projection. Now, because it's an obtuse angle, because this angle's obtuse, I think we got a dot product of what was it, minus 16 or something, or negative 1. So the negative tells you that it's great, you know, a bigger angle than 90. So that's why this thing's hanging out the back like this. So to do, I've got to warn you, to do these geometrically, I mean, that's a fairly straightforward calculation. But to do that geometrically is very, very difficult without the actually doing the computations. But there you go. Alright, any other questions? We want to do another example, perhaps? Or are we happy with this, or what do we think?
Another example would be great.
Okay, let's do another example, that's fine. That's why I'm here, so I'm just going to go and get this. Okay, sorry, I'm just going to muck around with my teaching subjects. Go and get that. 1. Yeah, I love all that. good. I need that one. Keep coming. Okay, so let's have a look at these. Alright, so let's just do a little bit of this because I've got a feeling that's needed. Okay, so the one that you might be most familiar with is that one, and we just did an example of this type where the angle's an obtuse angle. And so what we're doing here from this point to some point Q, and what we get is this vector A. So A onto B. And what that means is that we'll project A onto B. That's a right angle. A onto B, and effectively what we get at some angle theta is this bit here. Okay, so A onto B represents the distance. Okay, A onto B represents the distance P to Q. Okay, for a scalar. Okay, so that's your scalar projection. Now A onto B is the opposite of what we did previously. We did B onto A, didn't we? So see how they're reversed? So that's the trick of it. Okay, that's the trick of it, knowing that. Now where the angle's broader, greater than, so your dot product's negative or what have you, and your A and B are here, what you'll end up having is the distance between P and Q, and it comes out the back, and it's quite confronting. It's quite a confusing way to look at it. Okay, so picking that is quite an awkward thing, because here it was easy to say A, but I suppose we could do the sun shadow thing, you know, we could do the sun shadow thing like that, couldn't we? And say that that shadow was, but it's on the kind of the back of B. It's not on B itself, it's on the back of B. So that's the bit that's confusing. Okay, that's often very confronting. But once you get the hang of how to associate the projection language with the actual equation, they go hand in hand. Okay, so you've got to keep that in mind. And the vector projection is just it's just the vector in the direction of B. So it's like that's why we got this tiny little unit vector in the previous example. We got a tiny little unit vector that went that way. Okay. All right. So let's do another example. Okay. So let's go with this. I don't think that's exactly the same. See if you can do that. Okay, so the scalar projection. Now I'm deliberately doing them in reverse because I want you to get into the habit. Okay, because I think that's the awkward part of the whole thing, isn't it? Okay, so what have we got? We need the magnitude of B. So the magnitude's that one. We've got to do the A dot B. The A dot B. So A dot B is going to be sum of products. That was the language I used, wasn't it? I hope that's helpful. Is that helpful? Sum of products? So clearly the angle between them is they're pointing somewhat in the same direction. They're not at 90 degrees to one another, but nevertheless. Okay, and what we're asking for in terms of the scalar is that we want the length of this bit here and the length of that is 2 3/5. Okay, and then the other thing we want to find out is the vector projection. So the vector projection is going to be where we took the dot product and divided it by, multiplied it by the unit vector. So we did that kind of thing. What we can do here for the vector projection, this is the vector, let's call that point Q, and the origin. Now we've got this number here, 13/5, and so we've got to do that with the B. So we've got to find the B hat, which is B divided by, so the unit vector of B is B divided by its magnitude, which we didn't do separately and independently, it was just caught up in this calculation. So what did we say the magnitude of B was? 5. So 1/5, 4, 3, which is the same as saying 4 on 5, doing the expansion, 3 on 5, and so that's the B that we're after here. So we've got to do an expansion of this. So just multiplying fractions is easy. So 13 fours, 12 and 40 is 52, 25 on the bottom. It's a vector. 13 threes are 30, 39, and 5 fives are 25 on the bottom. So that's the length of our little unit vector in the direction of a projection onto A onto B. Did I write that anywhere? Oh yeah, I did up there. Whew, scared myself for a minute. A onto B. Alright, so it is a bit messy, but it is something you can do. I'm sure if you spend a bit of time now, you've got, hopefully that kind of helps you navigate the moving around of the parts, okay, with the language, and that's the real issue there, isn't it? But after that, the actual computations, the maths part of it, it's not that hard. I mean, no one should fail this subject. It's not that it's hard conceptually, it's just a big workload, and there's a lot of this rejigging of your thinking. And if you can get the rejigging of your thinking right, it'll all fall into place. Okay, so just be encouraged to keep there. All right, that's it? How are we going? Any questions? Any more? Filled up for today? All right, so, just be deliberate. Slow is fast. Be deliberate. Slow is fast. And, yeah. All right. If nobody else is going to speak, let's say goodbye. All right. Thanks for coming along. That's all right.
Thanks, Jason.
For coming along. And I'll see you next week. All right. Take it easy.